Hello. Today I thought I would tell you about a walk that I had with my wife yesterday, and I think it's quite relevant to this course, what we learned on this walk. So we often go for walks in the woods, and often we keep track of things, like how many of a certain type of bird we see or something similar to that. But yesterday we decided we would keep track of how far we had gone and how long it took us to go on this path. So I took a little notebook with me, and my wife has an app on her phone that keeps track of the distance that we've gone, and she has a clock that keeps track of the time. So we start out our walk, and I start out in my little notebook keeping track of the two things that we're going to look at. One of them is the time, and we decided we would keep track in minutes, and the other was the position we were along the path, how far we were from the start. So I decided to call that the variable s. And we decided, since the app was in meters, we'd put our measurement in meters. So we start out our walk, and just before I start, I put in its time 0, and we're at position 0 meters from the start. So we're walking along, having a good time, and at the end of exactly 1 minute, my wife looks at her app and she said, at the 1 minute mark, we had gone 8 meters. Now, you probably think that isn't an awful lot, but we're both over 70, so we have a little trouble getting going at the very beginning. Anyway, we keep going, and at the 2 minute mark, we're at 64 meters. So we're starting to get a little bit faster as we're going on. And at the 3 minute mark, we were at the 216 meters, and at the 4 minute, we were at 512 meters, and at 5 minutes, it turned out that we were exactly 1,000 meters from the beginning, 1 kilometer. And we're thinking, ooh, this must be a sign of something good. So we actually said, let's stop our walk, and I put my notebook in my pocket, and we ran back to the house, because we always like to analyze the data that we find during our walk. So anyway, I showed this to my wife, and she said, yeah, she's an artist, and so she said, that's just a bunch of numbers, and that's a little bit boring. So she took the pencil, and she said, I think we can display this better if we draw a picture. So she said, let this axis right here represent time in minutes, and let this axis represent the position in meters. And she said, we ended up going 1,000 meters and she made this nice picture, or graph, as we decided we should call it, because it looks like a graph. And time went for 5 minutes. So this was the first minute, second minute, etc. And she then, every time there was a data point, she would times 0, 0, 1, we were just barely getting started. 2, we were at 64, so still not too far up. At 3, we had moved up to 216. At 4, we were at 512. And at 5, we were all the way up to 1,000. So she, and I had to agree with her, she liked this better, and I said, yeah, that does look quite nice. I said, you know, the advantage of this is it has exact numbers in there, but if we use both of them, we've got a pretty good combination. So anyway, we could look at this and see where we were at 6 different points of time. But we really wanted to know where we were at other points of time. And we looked at it and say, well, we really don't have any other points. We could estimate it by finding somewhere in between. And by the way, my artist wife really wanted to do this. And then she said, now we can see exactly where we were from there. But I said, yes, but you really can't see what that number is. These are just 2 variables that don't really have any special relationship to each other. And she took a look at the numbers and said, just a minute, I think there is a relationship. If you take the t value and multiply by, or cube it, and then multiply by 8, you get the s value. And I tried some of the values, and sure enough, 3 cubed is 27 times 8 is 216. 4 cubed is 64 times 8 is 512. And it worked for every number. So what she told me is what we have here is a relationship between 2 variables. And we could call this one the independent variable t, and for every value of t, there is only one value of s. So she said what we have, what I remember, is a function. So she wrote up here, s is a function of t is equal to 8 t cubed. So now what could we do? We could find out our position not just at those 6 points in time, but we could find it at any time in that 5-minute trip. So we got our calculator out and we plugged in some numbers, and sure enough, we had all these different positions. And I said, now can we maybe have something to eat? Because I was getting hungry. But my wife said, I still would like to know more about our trip. I'd like to know how fast we were going. And I said, well, all we had on your app was our position. We didn't have anything about how fast we were going. We should have used a different app if you really wanted to know that. And she thought about it for a minute and said, just a minute, maybe from the data we have, we can find out how fast we're going. Because she remembered from her math class that the speed you're going is equal to the distance divided by the time that it takes. And she said the distance is just the time, or the distance. If I've got 2 positions, I can find the distance just by subtracting those 2 positions. So for instance, if you take time 1 and time 4, if you take those 2 points right there, she said if you take this distance, or this line right here, represents the change in position from time 1, that point, to time 4, this point. And she wrote down, she said the Greeks used the letter delta to represent change. So she said this could be the change in position, and then in this direction, this is time 4 and this is time 1. So this right here she called the change in time. And she said, if this is the distance that you went, and this is the time that it took you, if you divide delta s by delta t, you actually get the speed that you're going in meters per minute. And she even remembered that when you take this, which she called the rise, over this, which is the run between these 2 points, what we're really finding is the slope between those 2 points. So, wow, with data that had nothing to do seemingly with how fast we were going, we were able to determine how fast we were going between time 1 and time 4. We could just say the change in position is s of 4 minus s of 1, and the change of time is from time 1 to 4. And we already had these numbers. This is 512. The position at 1 was 8. So what did we do? We moved 504 meters in 3 seconds, or 168 meters per second. And we sure were able to find out how fast we were going in that time period. But we realized that we weren't always going the same speed. We kind of knew that from the beginning, because we felt like we were going faster as time went on. And sure enough, if you picked 2 other points, you get different slopes. So we were going at different speeds. So what we did is we plugged it in between time 0 and time 3, between time 2 and time 4, and we kept getting different slopes and we kept getting different speeds. And I was feeling that my wife was doing most of the work. So I interjected. I said, my physics friend said that there's another word that's better than speed. And I said, maybe this is a new, more hip word to use than speed, so we started to call it velocity. And we'll check in later if they're really the same thing, but they seem to be connected somehow. So what we were able to do is find the velocity between 2 periods of time. And that seemed pretty interesting to both of us. So I kind of wanted to stop at that point, but it wasn't getting interesting. And my wife said, she's kind of demanding. She said, can we really find out not this average speed, because that's really what we were finding was the average velocity or average speed. She said, I would like to find out how fast we were going right at time 3, right at this point right here. Well, I said, we've come up with a good method for doing this, but to really get this, what we could call instantaneous velocity, it's going to be pretty impossible, because to get the slope you need 2 points. And she kind of said, well, you're the math person, you should be able to figure something out. So my thought was, well, I want to make my wife happy, so I said maybe what I could do is just pick another point here really close to 3 and just find the slope in between those 2 points, and that should be close enough to make her happy. So what we did, instead of going from 1 to 4, we went from time 3.0 to 3.1. And there, the average velocity should be pretty close to the instantaneous velocity at time 3, because it's such a short period of time. Well, when I plugged that into the calculator, I got 223.28 approximately. So that's meters per minute. But she really wasn't happy. She said, that's not exact. So I said, I tried one more thing. I said, what if we do 3.01? Now, when we put it on the calculator, it came out to be 216 point, I wrote it down, 72 meters per minute. But it still wasn't quite making us, actually either one of us, happy at this point, because we thought it's really intriguing if we could only figure out a way to do this instantaneous. And she said, well, can't we even get closer than 1/100th to 3? Can't we come up, let's let the letter h be the distance, or be the time that we're going to go past time 3. In other words, we'll go from 3 to 3 plus h. And then you talked about limits when we were talking the other day on our walk. Can't we do this? Can't we take s of 3 plus h and subtract s of 3? That's the change in position from this time to this time. And the change in time from 3 to 3 plus h is just h. And then just take the limit as h approaches 0. And I had to agree with her that that made a lot of sense. I'm glad that I had talked to her a little bit about limits. So, what is s of 3 plus h? Well, we go back to our function, and that's 8 times 3 plus h cubed minus, well, s of 3 we already knew was 216. And I said, well, I can do the math. I can multiply 3 plus h times 3 plus h times 3 plus h. And I started to do that, and she said, well, I remember when I was in school, you could use the Binomial Theorem on that. You could just go 3 cubed plus 3 times 3 squared times h to the first plus 3 times 2 over 2 factorial times 3 to the first power. So that's 9h squared plus h cubed. And that saved us a little bit of time. I'm glad that she remembered that binomial expansion. It was starting to look pretty complicated. But then we realized that 8 times 27 is 216. So this cancels with this. And what are we left with? 216 times h plus 72 h squared plus 8 h cubed divided by h. And we realize that there's a factor of h in every term up here. So we can then cancel this h. We can factor out an h out of here and cancel. Now I can actually take the limit as h approaches 0 just by plugging in 0 for h. And what do I get? 216. We had figured out a way to find the instantaneous velocity at time 3. And that was really exciting. But guess what? My wife then wanted to know what was our velocity at other times. So I said, oh, how many times do you want to go through? This is taking us quite a bit of time to just do one. So she said, maybe what we can do, instead of putting 3 and then 4 and then 5, maybe we can call this t. So we can take the limit as h approaches 0 of s of t plus h minus s of t all over h, and let t just represent any point in time. So we're doing it exactly the same way we did here, except for letting 3 become a variable t. Well, what is this formula? It's 8 times t plus h cubed minus 8t cubed, s of t, all over h. And then at the end, we're going to take the limit as h approaches 0. Well, I wanted to see if I remembered the binomial theorem. So while my wife was watching me, I tried this one. Let's see. T cubed plus 3t squared h to the first power plus 3th squared plus h cubed. With a little reminder, I could still do the binomial expansion. And again, it was looking complicated, but what was the good part? I have 8t cubed minus 8t cubed. So I could cancel those right away. And then, besides that 8, I could factor out a h. So what does that leave me with? 3t squared plus 3th plus h squared. Oh, I forgot, I factored out the h. So now I can cancel those h's. I'm no longer dividing by 0, and now I can take my limit just by plugging h equals 0 into this expression. And what does that give me? 8 times 3t squared, so 24t squared, and these two terms drop out because h is approaching 0. Wow! What did we found an expression in terms of t. We have a new function. But it's no longer measuring the position, it's measuring the instantaneous velocity. So I have a new variable called the velocity in terms of time. And we have a new function. The old function found our position. The new function finds our instantaneous velocity. And we didn't even ever have to find out anything on our trip about how fast we were going. So we found this very exciting. And what did we want to do? Plug in some numbers. So we plugged in different times. At time 1, we were going what? V of 1, 24 meters per minute. At time 5, that was the really interesting one. How fast were we going at the very end? Because it felt like that's when we were going the fastest. So we put in 24 times 5 squared, which is 600 meters per minute. And we thought that's pretty good because in a 1 meter track, in a 400 meter track, this is 1.5 times around the track in 1 minute. And we figured it out, and it's just about the speed that Usain Bolt runs when he runs the 100-meter dash. And he was the fastest person in the world, at least a few years ago. So we felt pretty good that we were going that fast. So I really wanted to start dinner now, but one other thing we thought is maybe this would pertain to all functions. Maybe it doesn't just pertain to functions like we had come up with. So, and I'm just going to do this quickly now, and we'll go into it in more detail in the next video. But if I just have some function y is a function of x, if I were to take and call this point x, and this point over here x plus some amount h, the same h that we were talking about here, I could find that average rate of change of y with respect to x. But I could even do something more exciting. I could find the slope right at that point, the instantaneous rate of change of y with respect to x. And how am I going to do it? The same way. The rise over the run. The change in y over the change in x. But then, what are we going to do? That would give us this slope, and we really want this slope. So, to get the change in y, we're going to go f of x plus h minus f of x. And from here to here, the change in x is h. And we're going to take the limit as h approaches 0. And we know that we're going to come up with a new function in terms of x. So we decided to call it f prime of x. And since we derived this ourselves, we said, let's call this the derivative function. And the last thing before getting ready for dinner, we said, let's try it on one function. So let's take a fairly easy function like y equals x squared and plug it into this and come up with a derivative function. So we're going to call this f of x. We'd like to find the derivative function associated with this function. And we're going to call it f prime of x. So I'm just using this formula. Well, f of x is x squared, and f of x plus h would just be x plus h squared. So if I just now do the algebra, I get x squared plus 2xh plus h squared minus x squared all over h. Now the x squareds cancel out, and now I can divide this h into these two terms. And if I then take the limit as h approaches 0, I get 2x. And guess what? We have found the derivative function for the function f of x equals x squared, which gives us the slope of this curve at any point. So if I plugged in x equals 4, I would see the slope there is 8. So anyway, this was a pretty exciting day. We've discovered what a derivative is, and we're going to find that there's many other real important uses of this. So before I stop, I think I should give some credit, because I needed some help on this. This is my wife and my videographer and artist. So thank you for all the help.
Oh.
We'll see you next time.